mass energy distribution would curve the space-time, and one could make definite predictions of the observable consequences. So, although the theory sounds rather exotic and rather made up, it can make a number of. It has made a number of very interesting predictions, and all of this have been verified by several astronomical observations as well as laboratory tests. Let me give you a couple of examples. We know that light travels through a straight line, and that's because in the absence of gravity, the space-time is completely flat, and the shortest distance between 2 points in a flat space is a straight line. But this is not true if the space is curved. For example, if you connected points on the surface of a sphere, the shortest path is not a straight line, it's an arc, right? And it turns out that light travels to these what is called geodesics of the space-time. And when the space-time is curved, the light travels to the curved geodesic of the space-time. And this can have some very interesting implications. For example, imagine a star whose light is tracing the limb of the sun. And because the sun is curving the space-time around it, the light will follow a curved path. And the observer would see that an apparent shift in the position of the star. Of course, there is a difficulty in observing in everyday life because you cannot see stars during the day. But there is a time where you can see stars during the day, which is during a total solar eclipse. And basically, Arthur Eddington, a team led by British physicist astronomer Arthur Eddington, carried out a very remarkable expedition in the total solar eclipse on the 29th May 1919, which was almost exactly 100 years ago, to observe the position of stars during the total solar eclipse and to see if there is a shift in the position of stars as compared to their normal relative positions. And this is an actual photograph taken by Eddington's team. In fact, they sent 2 teams, one to Africa, south of Africa, and one to South of America. And this is an actual photograph taken by one of these teams, I think from the South African team. And if you look very carefully, you would see some of the stars come from this cluster of stars called Taurus. Since it's rather hard to see the actual position of the stars in this photograph, I have made a cartoon version of what Eddington's team have found. So, unfortunately, this picture is not very clear. So you would see this is the position of the sun here, and these blue stars are the actual position of the stars when the sun was not in between the stars and us. For example, you can make a reference photograph of the same cluster of stars when the same cluster of stars appear in the night sky. So after 6 months or something. Right? That is shown by these blue stars. Unfortunately, you cannot see the red stars here. So you should see, if the color of the prediction is accurate, you should see some other some red stars which are here, 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 which are the position of these stars that the Eddington's team observed during the eclipse. So, just to repeat, so this team made a photograph of this cluster of stars during the eclipse, just shown by these red stars are not seen here and here. And then they went back after 6 months or before 6 months, took another image of the same cluster of stars when they appear in the night sky, or when the sun was not in between us and the stars, which is the actual position of the star, just shown by this blue. And they found that during the eclipse, indeed, the position of these stars have been shifted to here, to here, to here, to here, etc. And moreover, you could actually, since you know the mass of the sun, you could exactly predict the shift in the position of stars using Einstein's theory, and these observations matched very well with the Einstein's theory to the accuracy of 10% or so. So this was one of the first remarkable confirmation of the prediction of Einstein's theory. And now, of course, we have been observing much more dramatic versions of this gravitational bending of light. This is an actual photograph taken by the Hubble Space Telescope, and you see this peculiar ring-like structure. What is here is what you see here is what is called a gravitational lens. So there is a very bright galaxy that is sitting here, and behind this bright galaxy is another galaxy. So there is a cartoon version of what is happening here. This is this bright galaxy. It is acting as a gravitational lens. So basically, it would curve the space-time around it, and the light rays would bend just as they are bent by a lens. And if there's a galaxy that is behind it and the observer is here, the light rays from this background galaxy would bend and form multiple images. And in this particular case, this lensed galaxy is just behind this lensing galaxy, the galaxy that is acting as a lens. So the observer, this galaxy, and this background galaxy are forming this particular in the line of sight. And the light rays from all directions are bent the same way, and this would form a circular ring-like image. This is called the Einstein ring. So these things have been regularly observed in astronomy these days, and in fact, they are not only confirmed. Now, astronomers are using the gravitational lensing as a powerful way of mapping out unseen matter distribution for the universe, such as the dark matter. So apart from verifying a prediction of Einstein's theory, gravitational lensing has become a very powerful tool for exploring the universe. So the gravitational lensing effect is not the only observable prediction of Einstein's theory. And according to Einstein's theory, not only the space is affected by the gravity, but also the flow of time too. Again, something is very hard to imagine. So Einstein's theory predicts that if you have two identical clocks, one sitting in a gravitational field and another far away from any gravitating object, these two clocks would run slightly differently. So the clock that is sitting in the gravitational field would run slightly slower as compared to the one that is sitting in the absence of gravitational field. So it's called gravitational time dilation. Again, there has been a famous experiment done in Harvard in the 1960s that verified this prediction, where they compared two clocks that are sitting only at a few meters apart and found that these two clocks are actually running at slightly different speeds. But this has become part of our modern technology now. I guess most of you use smartphones and Google Maps. If you want to navigate, you have to locate yourself in the map. And this is done by using what is called a global positioning system, GPS, which is based on using a system of satellites which form a sort of a fixed coordinate system around the Earth. And all these satellites have a very precise atomic clock on board, and these satellites transmit their location as well as the time required by the local clock. And a GPS receiver basically receives signals from multiple satellites and triangulate itself in the map. So that's why the GPS works. But now there is a catch, right? These satellites are are orbiting the Earth at several hundreds of kilometers away from the Earth. And hence they are seeing a different gravitational field as compared to the same clock on the surface of the Earth. Right? So before these satellites were launched, all these clocks were synchronized. But after they are launched, they are feeling a different gravitational field as compared to the gravitational field that is felt on the surface of the Earth. And as a result, these two clocks would run at different speeds. Of course, a very subtle, very, very minute effect. For example, the time lag between the two clocks is like 1 nanosecond per day. But if you do not take this into account, GPS will become inaccurate in a matter of few seconds, in a few minutes. So if the GPS has to work, it has to take into account these exotic predictions of general relativity that gravity affects the flow of time. There is also the prediction of special relativity that gravity, so the time is also affected by relative motion of objects. So GPS actually takes into account the time dilation due to the special relativistic effects as well as the general relativistic effects for it to work. So these exotic predictions have been not only verified by a number of observations, but some of them have become part of our modern technology itself. Now finally, so again there are a number of such very interesting prediction of Einstein's theory, including the existence of black holes, expanding universe, etc., etc., which I won't describe now. And the last observational prediction, last theoretical prediction that was verified by a direct observation is the existence of gravitational waves. So it turns out that if you solve these, what is called Einstein's field equations, which relate the geometry of space-time to the mass and energy distribution within the space-time, then these Einstein's field equations admit wave-like solutions. In a more physical way, I mentioned that if you have a massive object, it would curve the space-time around it. Right? And if this massive object moved, the space-time curvature also follows. Not only that, if this acceleration, if this mass distribution moves with an acceleration, changes in the space-time curvature will propagate outward with the speed of light, called gravitational waves. If you want another example, for example, we feel the gravitational field of the sun. That is what is making the Earth go around the sun. Right? And suddenly, suppose the sun were suddenly to disappear without leaving any trace. Then it turns out that that information can propagate to Earth only at the speed of light. And the Earth would feel the absence of sun only after 8 minutes after it has disappeared. So this fluctuation in the gravitational field is propagating at the speed of light. You can think of this as a gravitational wave. And the gravitational waves have very interesting properties.